So this is section 3.5, and what we're going to be working on is graphing square root functions and graphing cube root functions. So this is going to draw a little bit on things you learned when we were working with the vertex form of graphing quadratic functions. And key vocabulary for this section are radical function, so that would be a function similar to this: y is equal to a times the square root of x minus h plus k. That's a square root function. A cube root function would look like this: a times the third root of x minus h plus k. If you remember, when we graphed in vertex form, we had h and k. And then also parent function. This is also something we discussed in chapter 1 when we talked about quadratic functions. The standard form for a quadratic function is y is equal to ax squared plus bx plus c. But y is equal to ax squared is what's called the parent function for the quadratic function. In this case, y is equal to a times the square root of x, or y is equal to a times the cube root of x, would be the parent function of these two functions. So you notice it sort of takes off extra impacting parts. The key element of a quadratic function is that x is squared. The key element of a square root function is that x is, we're taking the square root of x. And the key element is that we're taking the cube root of x in a cube root function. So the parent function eliminates all the other little pieces that affect it. A typical sort of thing that you might look at is we've got this, this element here for drag racing. We've got a formula for calculating speed based on power, right? That's what this is. S is speed, P is power in horsepower, so the power of an engine. And it's a cube root function, so we can use this formula to answer this question. But first we have to learn how to solve cube root functions, so let's go ahead and do that. First we're going to graph. So this is a couple of square root functions. I'm going to graph them both on the same plane here. And these are in parent function form, so later we'll work with the full form. And what's key here in graphing is that when I make an input-output table, right, or a t-chart or xy table, whatever you want to call it, I am in control of picking my inputs. And I want to pick inputs that are going to be easy to do. Now, and what constitutes easy depends on the function. This is a square root function, so any input that I choose, I'm going to take the square root of it. So I'm going to pick perfect squares because those are easy to simplify. So I'm going to pick 0, 1, 4, and 9 because these are perfect squares, right? The square root of 0 is 0 times 1/2 is 0. The square root of 1 is 1 times 1/2 is 1/2. The square root of 4 is 2 times 1/2 is 1. And the square root of 9 is 3 times 1/2 is 3/2. And if I plot these points, 0, 0, 1, 1/2, 2, 3, 4, 1, and 9, 1.5, like that. You can see that I'm going to start here and I'm going to head on out in that direction, and this is sort of the curve that I get. Okay, so when we go on and do the other table, I'm going to change colors. I'm going to put them both on the same graph. Now I'm still taking the square root of x, so I'm still going to pick perfect squares, 0, 1, 4, and 9. That's one nice thing, is that I'm going to pick the same inputs every time for my square root functions. I'm going to pick the 4 smallest perfect squares that I know. So the square root of 0 is 0, times -4 is still 0. The square root of 1 is 1, times -4 is -4. The square root of 4 is 2, times -4 is -8. And the square root of 9 is 3, times -4 is -12. So if I plot these points, there's 0, 0, same starting point, but at 1 I'm at -4. At 4 I'm at -8. And at 9 I'm at -12 down here. And you can see that this curve is a little different. It follows the same basic idea. It starts from 0, 0, and it heads to the right. But two things that I want you to observe. First, the leading coefficient changes things, right? Just thinking about the absolute value of it, when it was small, like 1/2, it made a very flat graph. When it was larger, like 4, it makes a much taller graph. And also you'll notice that when it's negative, my graph goes below the x-axis, and when it's positive, it's above the x-axis. So this is the impact that happens by both the size, right, the basic size of the value for the leading coefficient, and whether or not it's positive or negative. Everything that comes after it, you see, is exactly the same. Okay, so let's take a look at cube root functions. We're going to have similar sorts of similarities and differences. So we're going to start with a negative leading coefficient. I am still the person in charge of picking the inputs. I still want to pick easy inputs, but since it's a cube root function, I'm going to pick perfect cubes. -8 is the cube of -2. -1 is the cube of -1. 0 is the cube of 0. 1 is the cube of 1. And 8 is the cube of 2. So these are all perfect cubes. When I go ahead now and plug these into my equation, right, the cube root of -8 is -2 times -5 is 10. The cube root of -1 is -1 times -5 is 5. The cube root of 0 is 0 times -5 is still 0. 1 times -5 is -5, and 2 times -5 is -10. So there's a certain symmetry to this. At -8, I'd be at 10. At -1, I'm at 5. 1, 2, 3, 4, 5. 0, 0. 1, -5. 1, 2, 3, 4, 5. And at 8, I'd be at -10. And this is what the graph looks like. It comes through here, zips through the origin, piles up that direction. Okay, so this is pretty much what a cube root function looks like. And let's go ahead and graph the other one, and then we'll talk about the impact of the leading coefficient on this. So again, it's still a cube root function. Perfect cubes are still perfect cubes. I'm going to go ahead and pick the same inputs. That should make it easier for you to remember what to do. Then I go through and simplify this. The cube root of -8 is -2 times 2 is -4. Cube root of -1 is still -1 times 2 is -2, 0, 2, and 4. Okay, so what this looks like, at -8, I'd be at -4, 1, 2, 3, 4. At -1, I'll be at -2. I still pass through the origin, and then 1, 2. And at 8, I'd be back to 1, 2, 3, +4. Okay, so this is sort of the standard look for a cube root function. If I graph the parent function, it would kind of look like this. But you can see again, the larger the absolute value of the leading coefficient makes it taller. The larger it is, the taller it is. You can see this graph is much taller than this graph is. But also the negative, you see, did the same thing it did to the square root function. It flipped it over. So it basically rotates the equation around the x-axis. It just flipped it over to the other side. Because my ends do opposite things, then which end is high and which end is low has changed because of the negative leading coefficient. Okay, so practice this graphing. Do problems 6, 7, 13, and 14, and then come on back to the lecture. So here are the graphs of the parent functions for a square root and cube root function. You can see this is the basic look of a square root function. It starts someplace, it heads out up and to the right. Because I can find the cube root of negative numbers, then this one does not stop at 0. So in a cube root function, it's going to go ahead and include negative numbers. We don't include negative numbers here because that would lead to imaginary solutions when I take the square root, and I can't graph imaginary solutions. In parent form, you can see the domain is x is greater than or equal to 0. And it's very easy to see on the graph. Where are my values of x? They start here and they go that direction. And the range is the y values. They start here and they go up. So x is greater than or equal to 0. y is greater than or equal to 0, right? The domain and range in a cube root function are all real numbers. And then here are the full forms of the square root and the cube root function that I discussed at the very beginning of the lecture. And the methodology for graphing these, and this is a methodology that we'll be using for a lot of different functions, so it really is going to help you to get used to it now, is identify what h and k are, and then put them aside and just graph the parent function. So if you just sort of break the function up right here and ignore everything that's to the right of the little line I've drawn in, that's what you're going to graph, and then you move it by h and k. Remembering h is always a horizontal change, k is always vertical change. Okay, so let's take a look at how that happens. So when we're taking a look at this item, oh, but wait, it looks so different. What's this to the 1/2 power? Well, remember the 1/2 power is a square root, so I could also write this problem this way. So this is in rational exponent form, this is in radical form. But these are both the exact same problem. Okay, I want to take a look at, this is a square root function. This is my form, x minus h plus k. So what's being subtracted from x here? That's going to be h. And what's being added on at the end is going to be k. -1 is being subtracted from x because x minus -1 becomes x plus 1. And 8 is being added on at the end. So if it helps you, h is always the opposite of what you see in the equation. K is exactly what you see in the equation. So then I'm going to now just graph the parent function, y is equal to the square root of x. Because I'm just working with the parent function, I'm still going to use the exact same inputs, 0, 1, 4, and 9, 0, 1, 2, and 3. And if I graph this, 0, 0, 1, 2, 3, 4, 2, 9, 3. This is what this graph looks like. Now, I need to move it by h and k. So I'm going to move each point 1 to the left and up 8. So 1 to the left and up 1, 2, 3, 4, 5, 6, 7, 8. There's that point. 1 to the left and up 8. 1 to the left and up 8. And 1 to the left and up 8. And now here's my final graph of the full equation. See, it has the same shape as this, but it's just been moved 1 to the left and up 8. We can do the same thing with a cube root function. Again, I want to start off by identifying h and k. In this case, h is -7 because this is x minus -7, and k is -6. Then I'm going to ignore it, and I'm going to graph this parent function. Y is equal to -3 times the cube root of x. Again, my inputs aren't going to change. I'm still just graphing this cube root function in parent form. So this makes it really easy. You keep picking the same inputs every time. And then the outputs change a little bit based on this leading coefficient. So this would be 6, 3, 0, 3, -3 and -6. So at -8, I'd be at 6, 1, 2, 3, 4, 5, 6. At 1, I'd be at 3, 0, 0, 1, -3, and 8, -6, 5, 6 right there. And I'm going to go ahead and pop through with this. This is the graph of the parent function. Now I'm going to take each point and I'm going to move it left 7 and up 6. Oh, well, that's going to be a little complicated because of where I've got my graph, and it's going to be difficult. Let me move this over, give myself a little more room. Left 7, sorry, 1, 2, 3, 4, 5, 6, 7. Right, so left 7 and up 1, 2, 3, 4, 5, 6, about here. Left 7 and up 1, 2, 3, 4, 5, 6. Left 7 and up 1, 2, 3, 4, 5, 6. Left 7 and up 6. Let's see, 1, 2, 3, 4, 5, 6. and left 7 and up 6. 1, 2, 3, 4, 5, 6. And this is what my final graph is going to look like. Okay, so go ahead and practice this. Do problems 16, 19, and 22, and then come back to the lecture and we will take care of this word problem. So when we take a look at this particular problem, they would like us to graph the model. So this is probably something, when you start looking at these numbers, this is something that is intended to be done on some sort of a graphing tool, like a graphing calculator. These are kind of odd values. But I could go ahead and I could begin by picking perfect cubes again. I'm going to do, right, I have P is X and S is Y when you look at the way this problem is set up. So if I pick inputs that are perfect cubes, I could get outputs that would be simple to work with. So I would probably pick 0, 1, 8. You'll notice I'm not picking negative numbers because really, would we use negative power? We would not. Okay, so that's something I wouldn't really worry about. If I look at 3 cubed is 27. 4 cubed is 64. So if we take a look at this, I'd have 0, I'd have 14.8, I'd have 29.6. I'd have, let's see, 3 times 14.8 is 46.4. And then 4 times 14, 40, 56 plus 3.2 is 59.2. So we're moving along, but you can see we're not really getting to the 200. If I want to solve specifically for the 200, I would go ahead and set 200 as my speed is equal to 14.8 times the cube root of P. I would take 200 and divide it by 14.8. And that gives me 13.51. So 13.51 would be equal to the third root of P. And then I would cube both sides of my equation. So if I go back to my calculator and I go ahead and cube it, it's 2467.77. So basically 2468. You can see it would have taken me quite a while just going up by perfect cubes. So if we were to use a graphing calculator as the problem suggested, it would be pretty quick to find all of the solutions. I've gone ahead and plugged this function into the Desmos graphing calculator that I use online. And I'm looking for, this line here is 200. So where does my graph hit 200? And you can see it's way out here, right about, I would read this as very close to 2500 if I that's 2500, 199. That's really close. So 2510, 200. There we go. So another way to go about solving the problem, but the key here is when I'm solving this problem, I have to get rid of a cube root, I cube both sides of the equation, and that allows me to go ahead and solve. Alrighty, so that is the end of this section.